Hello everyone, my name is Cheyenne, and in this video I'm going to talk about a torsion problem in strength of materials. So the question says the motor shown below supplies power at a rate of 150 revolutions per minute. So we know that this is basically the N value, right? So when we are finding the power formula, when we know the power formula, it's 2 pi N T over 60, and this is N. Of course, we're going to talk about it later, but just as we go, we can extract information as well. And of course through shaft AB. So this is the motor, and of course it supplies power through this shaft. And gears D, E, F, I, and K supply power to multiple machines. So these are all D, E, F, G, I, K. These basically supply power to multiple machines. And of course there's a relationship given between basically the gears, the torques that these gears have in this shaft. So gear C, D, E, F, G. And additionally, the maximum torsional stress in portion FG is 15 megapascal. Now, this information is key, right? The maximum torsional stress is 15 megapascal because from somewhere because the power is not given, so from some positions, from some location here, we have to extract some torque data, so that we can have our torques for the gears as well as the torque for the shafts, and we can of course draw the torque diagram. So we should get that information from somewhere, and this is the key information, right? It says the maximum torsional stress in portion FG is 15 megapascal. So we'll use that information to basically find all the other torques, right? So the questions are basically going to be solved, it's just a matter of using the formula. So determine the power of the motor, determine all the torques for all the gears, and draw the torque diagram for all four shafts. Finally, find the friction force. So for all of these, we need the torque values, right? And we're going to talk about it later. Determine the maximum torsional stress in each shaft, considering the shear strength, find the factor of safety, and calculate the shear flow in shaft JK, which is a thin walled section here. And here, of course, the data we have, right? A, B, C, D, E. These are both solid circular sections. EFG is a hollow circular section. HI is a solid rectangular section, and JK is a hollow thin walled section, right? And then, of course, the question also asks about the rotation of one point with respect to another. For that, also we know the formulas. And at the end, it says if we were to use a different geometry for the material, what would be the maximum shear stress, right? So let's start with the first question. So we are basically going to start solving our question with finding the torque values for all basically parts, right? So for part A, B, C, D, D, E, E, F, F, G, for all of them, we're going to find basically the torque values in the shaft. So this is summary of information, right? So for the first question, we need to basically find all the torque values. So where do we start from? The question says tau FG, the maximum shear stress in portion FG of shaft CDEFG, is 15 megapascal. Okay. Now, basically this has a direct formula, right? What is the formula for this? It's TC over J, right? TC over J is the formula. So here it is. So this is our circular shaft, right? This is our hollow circular shaft. Remember, part FG, here it is. Part FG is a hollow circular carbon steel shaft with outer diameter 100 millimeter and the thickness of 15 millimeter. So it's very important to know that the inner diameter will be 70 millimeters, okay? Because the thickness, we have like one thickness at the top, one thickness at the bottom. So basically our inner diameter is 100 minus 2 times 15, okay? So remember to avoid that mistake. So it's 15 millimeters thickness, it means 2 times. Basically, the inner diameter is 100 minus 2 times the thickness, okay? So the inner diameter is 70. So the formula is TC over J, right? TC over J, so TFG, C over J. So from the formula, we know what is J. J is pi over 32. The outer diameter to the power of 4 minus the inner diameter to the power of 4, millimeter to the power of 4. And of course here, you see megapascal here. Megapascal is Newton per millimeter squared. So what I've decided to avoid any type of conversion, I basically considered all my units to be newtons and millimeters, right? So there's millimeters here, millimeters to the power of 4, and my torque that I'm going to find is going to be in Newton millimeter, which I'm going to basically convert later, right? So from here, again, like what is this C, right? So we know J, the formula for J, this is the polar moment of inertia. C is the radius, right? The maximum radius we're looking for here. The maximum radius is 100 divided by 2 or 50 millimeters. And TFG is the torque in that portion FG. So based on this formula, I'm going to get my T or my torque for portion FG in Newton millimeters. And this is the value I'm getting, right? And of course, if I multiply this by 10 to the power negative 6, I'm going to get the value in kilonewton meters, right? One of the 10 to the power 3 is for milli, and the other one is for kilo, right? So I get 2.24 kilonewton meters. But there's a point. So we'll say, okay, so I found one of the torque values, right? This is TFG. I have the torque value for portion FG. But the question, so based on this, I really can't find any of the other values because the information here that I have is the relationship between gears, right? So this TF is equal to 1.5 TG, right? So the relationship is given between TG, TF, TE, TD, TC. It's not about TFG, right? Remember that the torque value that you have for a portion is relevant from, but it's not really relevant to TF or TG, TE, TD, TC. Of course, there's a relationship when you're drawing the torque diagram, but it's not directly. It doesn't mean that, for example, TF is equal to TFG. However, here we know that because this is the end of the shaft, right? So from TF, we go to TG. So we have a value from the torque diagram here. And TG should be either going down or going up to 0, right? So at the end of the day, the point is TG, the absolute value of basically TFG is equal to TG, right? Why? Because whatever value you have here, you're going to basically go TG up or go TG down to 0 because our shaft is in equilibrium. Basically, it means that in general, whenever you are looking at a shaft from the left side, right, from the left end or the right end, the magnitude of, for example, here in this case, TC is equal to TCD, right? It's basically simply derived from, we can think about it from the torque diagram perspective, right? I mean, we're trying to draw the torque diagram, so this is going to make more sense. So TC is equal to TCD, and from here, from the right side, TG, right? TG is equal to TFG, right? In terms of magnitude, of course, right? So here we can see that TG is equal to TFG, right? But you say, okay, what about the signs? So you just say the magnitude, and we're going to say, you know what? Is there any signs here? Like, are there any signs here? No, there's no sign. So what I will do is just to basically assign an arbitrary sign here, right? So that I can get rid of all the, extra assumptions that I'm going to make later, right? So here, if I basically make an assumption and I put a sign here, so here it is. So let's say this is the direction at which I am supplying the power from the motor, right? This is the torque. For the shaft AB to be in equilibrium, this basically gear B, the torque should be going the opposite way, right? Because the shaft is in equilibrium. And if this is going down, just based on common sense and common knowledge, this is going to go the opposite way, right? That's the way it is. Like, this is basically based on the forces between the teeth of these gears. If this is basically turning down, this is going to go basically up, okay? But here for shaft CDEFG, if shaft C is basically getting the power from AB, so this is the supply gear, right? This is supplying the torque, and torque, this is the gear D, E, F, and G are taking away this torque value, right? Whatever is supplied. So if this is going up, all the others should be going down because they're taking away the torque. This is the basically main supply of power. And this is going down, 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 down. So if this is going down, H and J both should be going up. If H is going up, I should be going down because, again, the shaft is in equilibrium. And again, J should be going up. And if J is going up, K should be going down because the shaft is in equilibrium. So this is the way we just determine the signs. So from now on, we're not concerned about the signs, right? We are just going to draw our torque diagrams based on the signs that we have here, right? This is based on what we determined. Of course, you could have, determined, basically assign your torque, basically direction at the start differently. But, of course, all the signs will be opposite here. But, the point is to be consistent, right? We have to be consistent with our assumptions, okay? So here, after we do that, we say, okay, so we found we basically said that TFG that we found is equal to TG. So based on the formulas that we have here given in the question, we can say that, okay, so we know TG, so we can find TF, we can find TE, we can find TD, right, based on these values. We can know the magnitudes. Again, remember, we're not concerned about the signs here, so don't be concerned about the signs. Oh, we have all the signs here, and when we're drawing the torque diagram, everything will be basically direct and clear. So here, we found TG, so we have the formula for TF, we have the formula for TE, and we have the formula for TD. So now for the shaft CDEFG, we have 4 values, TD, TE, TF, TG, right? And by the way, we can also see that the sign is also the same, although like not really important, but you see like TG, TF, TE, TD, they have the same sign. But what about TC? How can we find that? Well, we have here 4 gears, 4 torque values. Basically, sorry, 5 torque values, and we have 4 of them. So basically we can use the equilibrium equation for this shaft to find TC, right? So here, if we want to, basically we have this information, we can say, okay, for the shaft to be in equilibrium, TC, which is in this direction, is equal to TD plus TE plus TF plus TG. So if we write that equation, we'll end up with TC equals 12.88, right? So the TC is 12.88 up, and so yeah, here it is. So this is the value, see, 12.88 up, the other is 2.8 down, 4.48 down, and as you see, the rest. Here, now we are prepared to basically draw the torque diagram for this shaft, right? CDEFG. We have all the torque values, we have assumed all the signs. Now we are prepared to draw all, basically the torque diagram, basically for all of them, but of course we will need gear ratios for later, to basically draw the other torque diagrams. But for now, this is enough to basically draw the torque diagram for CDEFG. As we have done before, the positive convention that we assume is always, if this is your thumb, this is basically going forward, right? So your hand is going forward. So this is the positive direction, right? So basically we mean that this is the positive sign for our torque diagram and this is the negative, right? So it means that this is going up in our torque diagram and this is going down. So the way we draw our torque diagram, of course, we draw our graph, and here at point C, we go 12.88 up. So we go 12.88 up. But after point C, so from point C to D, constant, 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 and then at point D, we go 2.8 down. So we go 2.8 down and we end up with 10.08. And then a constant, constant, and then here again we have another torque, 4.48 down. So again we move 4.48 down. Again at point F, we go 3.36 down. At the end, we go 2.24 down. A good check to basically see if our torque diagram is correct is to basically evaluate if at the end, do we get to 0? If we get to 0, our torque diagram is 99% of the time correct, right? So that's a good check to remember. So this is a torque diagram for portion CDEFG, and we'll use this torque diagram to basically plug in the values that we need for the maximum shear stress, for rotation formulas, and everything else. Now, basically we can use, now that we have basically TC, we have TG, and we have all the other values, we can use gear ratios, right, to find TB and TA later, and from TG we can find TH and TJ, and later TI and TK, right? So now we are prepared to basically find all the torque values and all the torque diagrams. So we know this formula, right? TB over DB, TB over diameter of B, and remember, when I say DB, it is the diameter of the gear, right? It has nothing to do with the shaft. So here TB over DB is TC over DC, right? So diameter of the gear is given 300, so TB over 300 is equal to TC over 200, right? And TC is known, we found it before, so from here we can get our TB value. If we get our TB value, by the way, right, if this is TB, we know TA as well, right? Because this shaft is equilibrium, we know TA is equal to TB, right? Based on simple equilibrium, so we know TA as well. But yeah, before going to even calculate like TH and TJ, we're now basically prepared to solve for the power, right? What is power? It's T times omega, right? Torque times the angular velocity. But we have a simpler formula, like we have the conversion, right? Basically, this is the conversion, but of course you can use this formula as well if your N is in revolutions per minute and your torque is in Newton meters, kilonewton meters, doesn't matter, right? But of course, this is the conversion that we actually use. This is where this formula is derived from. So you have the torque value, 2 pi n t, right? Basically, it's 2 pi n t over 60, right? So from here, I have Newton meters. I will get 303.48 times 10 to the power 3 watts, right? Or 303.48 kilowatts. So this is the power that this motor supplies, right? So basically, this is the power. So this is the answer for one of the questions. So now we are prepared to basically go and do the other ones as well. So we have TH and TJ. We can find that. So TH over DH is equal to TG over DG. We know DG, we know TG, we know DH. So we can find the value as well as TJ. This is the same thing we did, right? TJ over DJ, right? TJ over DJ is equal to TG over DG, right? And we know TG, we know DG, we know DJ. So from here we can find our TJ and TK value. So now as you can see, we have all the values, right? We have all the values here, 19.30. So we have all the values here for all the gears. So now basically we can draw the torque diagram for all of them, right? But now that we know this, before even doing that, we can find the friction forces, right? Because if you remember, the first question was to determine the power. To determine the power, we needed to know the basically torque that's supplied from the motor, right? And we did that by basically finding TC and then using gear ratios to find TB, and then we found TA. So based on that, we used the power formula 2 pi nt over 60, right? To basically find our P or power value, right? But the next question was find the friction forces. Well, to find the friction forces, this is basically the force between the teeth of the gears. We need the torque value, right? And we need the radius of each gear, right? And we do have that as well, so we can calculate that as well. So this is basically the between, like, it shows basically an illustration of the forces between between basically gear B and gear C, right? So basically the torque is created because of the force between the teeth and the radius, right? But see, torque is a kind of, you can kind of think of it as moments, right? It's kind of like the force multiplied by this kind of like a radius, right? But of course we call it torque because it's kind of like a turning, it's like a kind of related to torsion rather than bending or flexure, right? So it's torsion. So here we have force multiplied by the radius of each gear. So this F, let's say BC multiplied by R gives us this torque. And if CB multiplied by this radius gives us basically this torque, right? So here we can use either of them. So we can use either 19.32 divided by the radius of this gear, or we can use 12.88 divided by radius of this gear, right? So, and both of them will give us the same value because this is kind of like action and reaction, right? So these two values are the same thing. So here we use we use TB, right? So we said TB over RB is equal to 19.32 over 0.50. Of course, remember that we are using consistent units, right? So we say 19.32 kilonewton meter divided by 0.50 meter, meter and meter cancel out, and we end up with 128.8 kilonewtons, okay? So it's the force between the two gears. For gears, basically H, G, and J, this is how it goes, right? So this is the force here, this is the force, and same as we did before. So our F, H, G, J, all these forces are equal, right? And we can use either TH over RH, TG over RG, or TJ over RG, right? So any of them. So here we decide to use TH over RH. So 3.73 divided by 0.125. Again, where do we get 0.125? It's the diameter of the gear divided by 2, right? Of course, in meters because we want to be consistent in terms of our units. So from here we get the force basically that we have here, right? And all of the other forces. Now, we can basically draw the torque diagram, right, to finish the first question, right? The first question again was to determine the power, to determine the friction forces, and also draw all the torque diagrams, right? And we are now in the last step. So here, this is the shaft AB, if you remember, shaft JK, which was at the bottom right, and shaft HI was at the top right. So here, again, this is the torque, and here we have 19.32 up, and then it goes like that, and then 19.32 down. So this is a pretty simple torque diagram. So same thing for JK. So it goes 2.99 up, and then 2.99 down. And again, for this one, 3.73 up and 3.73 down. Okay. So we are now prepared to go to the next question, which is talking about the maximum torsional stress, finding the factor of safety, and other rotation values. And we are prepared to do it now because we have all the torque diagrams, right? It's very important because for maximum torsional stress values, for rotation values, we do not use gear values, right? That's a very important point to remember. We use the shaft, basically the shaft value. So here we have 90.32. Of course, for shaft AB, it happens to be the same because it's a very simple shaft, right? So you have 19.32 for point A, and you have 19.32 for AB. But in shafts like as we saw for CDEFG, that might not be the case, and we'll see that later. But it's again, like, keep that in mind that we need the torque diagram to basically use it in our formulas for TC over J, for whatever else. So here we'll start with shaft AB, right? Because the question says determine the maximum torsional stress in each shaft. So we're going to evaluate each shaft. So start from AB. So here for AB, what is the formula? It's solid circular shaft, right? For solid circular shaft, we know the formula is TC over J, right? TC over J. What is T from the diagram? We know it. 19.32 times 10 to the power of 6 Newton millimeters, right? Again, we know the conversion, 19.32 kilonewton meters or 19.32 times 10 to the power of 6 Newton millimeters, okay? Multiplied by C value, right? What is C? This is the radius, right? The maximum radius, Y max, because we are looking for the maximum shear stress. So the maximum radius is 100 divided by 2, or basically 50 millimeters that we have. And here, this is the J value, pi over 32 times diameter to the power of 4. Again, this is the J for a solid circular section. And as you can see, I have used all my units as Newton, millimeters to the power of 4, so that I will end up with Newton per millimeter squared for my stress, or megapascal directly, which is the most common unit of reporting stress values. So from here, I get my tau AB, basically the maximum shear stress for portion AB. Now I'm prepared to basically find my factor of safety. For the shear strength given for steel is 300 megapascal. So I will say 300 megapascal. We know what is factor of safety. It's allowable divided by applied. So 300 megapascal divided by what we found is 3.05, greater than 1, so it's okay. Now we can move to shaft CDEFG, right? For shaft CDEFG, we cannot basically just use the highest value, right? So we cannot just say, okay, it's TC over J. And, you know, like I have like 12.88, 10.08, 5.6, 2.24. So I will say, okay, 12.88 is the highest value, so I'll just use it in the formula, right? I cannot do that. What is the reason? The reason is portion EFG has a different geometry, right? So it has a different J value. So I will have to treat CDE differently from EFG, right? So I have to basically find the maximum for this portion and maximum for this portion, okay? So here, let's start with portion CDE, which is a solid circular section. So the highest, I need basically the highest torque for that one, right? Again, what is the formula? As we did before, TC over J. But I would say, okay, for CDE, which one is higher, right? Do I need to calculate like DE as well, or CD is enough? Of course, CD is enough, right? Because for CDE, the geometry and everything else is the same, right? So I might as well just use the highest value, right? The highest torque value. Because obviously we can see that if we use 10.08 here, we're going to end up with a smaller value, right? So 12.88 is a governing factor here. So 12.88 multiplied 10 to the power of 6 Newton millimeters multiplied by 50 again. Again, the diameter of the shaft in portion CDE is 100 millimeters. So the radius is 50. And it is the J value as we discussed before. We end up with this value. Now we need to find our stress value for portion EFG. So what is the maximum stress value for that? Well, we'll say, okay, again, it's going to be TC over J. But again, for EFG, the geometry is the same. So we'll say that, okay, I'm just going to use 5.6, right? Because I know that 2.24 will give me a lower value. So here, again, I have TC over J. I have T, the torque value. I have C, the radius, the maximum radius. Again, remember, when we're talking about hollow section, again, the maximum radius is 100 divided by 2, right? Why? Because this for portion EFG, as you can see, the outer diameter was 100 millimeters and the inner diameter was 70 millimeters, right? Or 100 minus 2 times 15. So when we're talking about the maximum stress, we're talking about the outer diameter. So outer diameter divided by 2 is this one. So 100 divided by 2 is 50 millimeters, right? Same as we had before. But here's the difference, right? Here's the main difference. The J value is pi over 32 times the outer diameter to the power 4 minus the inner diameter to the power 4. Okay? That's the main difference from the solid section. And when we write this again, remember we are using Newton millimeters to end up with megapascal. So we end up with this value. So after basically seeing these two values, we can see that, okay, for shaft CDEFG, the governing stress was actually 65.60. So here is, so we basically determined that is the highest value. Now we can basically determine the factor of safety, and the factor of safety is 300 over 65.60. It's higher than 1, so it's fine. Now we can move to shaft JK and HI, all the other ones, and determine the maximum stress there. So for shaft JK, what type of shaft is this? So this is a hollow thin-walled square tungsten shaft. Hollow thin-walled square. What is the formula for a hollow thin-walled square shaft? Right. So this is our section, right? So this is 75 millimeters is the width of the. And of course, this is wrong, of course. Yeah. So this is a square section, so it's 75 times 75. Okay. So this is like a typo. And the thickness is 5 millimeters, right? If the thickness is 5 millimeters, it means that the inner, basically, side is going to be 75 minus 2 times 5. But let's see, what is this? This is the width, or each side of the square for the median section, right? The median. Why do we need the median? Let's look at the formula. The formula for a hollow thin-walled section, whatever the section is the torque divided by 2 divided by T divided by AM. What is T? The thickness. At a point we are calculating the stress, right? So for example, if we're calculating at this point, the stress might be different, right? The stress is affected. But in this case, the question is that has not mentioned anything, and we don't actually. The question doesn't really need to mention anything, because here all over the place, as you see, the thickness is the same, right? If, let's say, for example, in this section the thickness was different from this section, the question should have specified. But in this case, we don't need any specifications because the thickness is the same all over the place. So this is the torque, this is the thickness. AM is the area of the median. Basically, here is square, right? Area of the median is square, right? The median square is the square that goes in between, right? Exactly in the middle of the inner square and the outer square, right? So this is that one. And what is the side for that? It's 70. Why is it 70? Well, the outside width is 75 and the thickness is 5. So we go 2.5 from here, 2.5 from here. So 75 minus 5, we end up at 70. Okay. So we know TJK, right? We know it from our torque diagram. So 2.99 times 10 to the power 6. And we know 2 times 5, right? We know the thickness is 5 all over the place. But what is area, right? Area, as we found, it's 70 squared, right? Because it's a square. So 70 squared is the area of this median square, right? 75 minus 5. Okay. And of course, here this is also a typo. So this is going to be millimeters squared, right? 2 times 5 millimeters times 75 minus 5 squared, millimeters squared, right? It's very important. And of course, we're going to end up with 61.02 megapascal, right? Again, as you see, I've used units Newton millimeters, so I'll end up with Newton per millimeter squared or megapascal. And of course, we can calculate the factor of safety. The shear strength for the tungsten section is 400 megapascal, and the applied stress is this, so it's greater than 1, so it's okay. And now we can move to shaft HI, which is a rectangular bronze section with a width of 50 and a depth of 150 millimeters. And the formula for this, the maximum stress for this, is T over alpha A squared B, right? T is the torque value for the section, which is 3.73, right? So you can put it there. So let alpha be there for now. So we'll talk about it later. A is always the smaller dimension here, right? The smaller dimension 50, right? 50 in this case squared. B is the larger dimension, right? For the rectangle. So it's 150, we'll just put 150 there. Alpha here is derived from the table that we have in most of the strength of material books based on the B over A value. So in this case, B over A value is 150 over 50, which means that 3, right? For 3, we can go to our table or to our figure, whatever we have, to get our alpha value, right? So this alpha value 0.267 is for B over A value of 3, okay? So you can check that out as well. So basically, if we do the calculation, we end up with this value, and we can calculate the factor of safety as we've done before. The shear strength given for the bronze, section is 240 megapascal in this question. We divide by the applied stress, so we end up with this value, which is greater than 1, so it's fine. The question also talks about calculating the shear flow in the thin wall section. Okay? And we know what is the shear flow. Shear flow is basically the force per unit length. Force per unit length. Or we can say that the shear flow is stress, right? Shear stress multiplied by the thickness, right? That's also another formula for it. So we can say, okay, what was the stress that we found? It was 61.02, right? If you remember in the previous page, here we found 61.02 for the thin wall section, right? So we know the stress at basically at any point in this section, right? So we can say that, okay, here I have 61.02. Of course, when I say for any section here, it's very important. So this is the average stress, right? So the formula that we have is for average stress, right? That's the formula we know, right? So we can calculate our shear flow is also based on this average stress. So 61.02 multiplied by 5 millimeters, right? Stress multiplied by thickness is going to give us 305.1 Newton per millimeter, right? This is our shear flow. So shear flow is constant, as we know, all over the place, right? So from here, it doesn't matter. The shear flow is the same. Based on thickness, however, of course, our stress can change, and we can see it in other examples, of course. The last, basically, portion of this part of the question is talking about rotations. So the first question is rotation of A with respect to K, okay? So here, this is the formula for it, right? So of course, there's no specific formula for calculating, but this is how it goes. So we start with portion A. So we want to find theta A with respect to K. So we say, okay, we start from this point. So we say theta A with respect to B, okay, plus. There is a transfer between the gears. How can I account for that? Well, what we'll always do, of course, you can go back to the strength of material books or your lectures, and you will see that there is a relationship between the radius and diameter and between the rotation, right, the theta. And you can see that the relationship between the rotation and diameter is basically inverse, right? They're inversely proportional. So based on that, you can basically remember, right? Of course, you can find it based on that formula as well. But you can remember that, okay, whenever you're moving from whatever place, so let's say we're moving from point A to K, I will say theta A with respect to B, plus diameter of the next shaft that you see, right? The diameter of the next gear, right? DC, right? DC over whatever I'm coming from, dB, multiplied by whatever rest we're going to talk about, right? So it's very important you can remember it like that, theta A with respect to B, plus DC over dB, right? Next one over the current one, okay? This is how you can remember it, okay? So I have theta A with respect to B plus DC over B, dB, multiplied by all the rest of the torques, right? Whatever I'm going to calculate, right? So I open the parentheses, and I'll say, okay, theta C with respect to D, plus theta D with respect to E, plus theta E with respect to F, plus theta F with respect to G, plus, again, we'll do the same. Next diameter over the current diameter. Next diameter, dj, over the current diameter, multiplied by theta j with respect to k. Okay, and now I am able to basically close my parentheses, right? Now that I know this, I can basically, write all the formulas and just substitute the values. So theta a with respect to b, what is AB? AB is a solid circular section, so TL over JG. I have sections CD and DE. These two portions are basically also solid circular sections. So again, I have TCD LCD plus TDE LDE over G is still JCDE. Plus EFG is of course, again, in this case, it's a hollow circular section. Of course, J is different, so that's why I separated these. So TE, basically TL, again, TL over JG, GJ, right? Plus, I go to here, theta J with respect to K. So JK is a hollow thin-walled section, right? Hollow thin-walled section. For this hollow thin-walled section, I have this formula. TL over 4 area of the median squared times G tungsten multiplied by the integral over area of ds over t, side over the thickness. And we're going to calculate all of these later, but basically in the next page. So now we can basically simplify our formulas, right? So this was the formula that we had, right? So now we can basically substitute the values, right? So we can say that 19.32 times 10 to, so this is for AB, right? So this that we can see, right? This is for TAB. So this is basically this one, right? So TAB, this is from the torque diagram, right? That we had here for AB, multiplied by the length, here 4 meters, divided by G, which is the modulus of rigidity for steel that was given in the question, multiplied by J, which is pi over 32 times 100 to the power 4, multiplied 10 to the power negative 12. So remember that we are using Newton and meters here because we want to end up with radians for our rotation values, right? So it's multiplied by 10 to the power negative 12. Why? Because it's milli, right? So 10 milli, which is 10 to the power negative 3, to the power 4, it's 10 to the power negative 12, right? So we have to convert it to meters to the power 4. And then the rest, right? So basically this is DC over dB, DC over dB, here it is, multiplied by TCD LCD plus TDE LDE divided by this. So we have TCD LCD, so we have these values from the torque diagram and the figure, right? So 12.88 times 10 to the power 3. Again, why does it 10 to the power 3? Because we are using Newton meters, right? It's 12.88 kilonewton meters. We convert it to meters, Newton meters, right? Multiplied by 5 meters plus 10.08 times 10 to the power 3 times 5 meters again, right? Divided by G, this is again the modulus of rigidity for steel, right? Which is for section CDE. And multiplied by the J value, pi over 32 times 100 to the power 4. And this, of course, the J value for a solid circular section. Of course, multiply 10 to the power negative 12 because we want to convert it to meters to the power 4. And we say, okay, plus EFG. So EFG is a hollow circular section. Again, you see TL, right? TL, right? As we know before. G. But the difference, of course, we know is J, pi over 32 times 100 to the power 4 minus 70 to the power 4 multiplied by 10 to the power negative 12. So we've done this before as well. Now, the different part, which we have not seen before really, is this one, right? This one. So how can we deal with this? So at first we have dg over dg, simple enough, right? dg over dg multiplied by, we have here tjk ljk based on the formula. Tjk, we know it for the torque value for this, times ljk, right? The length, 6 meters. Now here we say divide by 4 am squared. Okay, 4 am squared. Remember what it was? So for am we had 70 squared, right? Or 75 minus 5 squared was our a. So or 70 squared, right? 70 squared was our am, right? The area of the median. Now this is am squared, right? It's very important to notice this. Am squared. So it's 70 squared is squared, or 70 to the power 4 millimeter to the power 4 actually, right? So this is also millimeter to the power 4, right? This is also a typo, which is converted to meter to the power 4, right? Times 10 to the power negative 12. Why? Because it's milli, 10 to the power negative 3 to the power 4, right? It's 10 to the power negative 12 is the conversion. Multiplied by 160 times 10 to the power 9. This is the modulus of rigidity given for tungsten, right? Because we know section JK is tungsten. So this is the G value, right? G tungsten, as we had. Now multiplied by integral over area of ds over t. What it means is that we have to sum up all the sides that we have, all the area that we have for that section, right? If you remember, we have a thin-walled, hollow section, a square section. ds represents the side, t represents the thickness, right? So if you remember, each side of the median, it was a square section. Each side of the median was 70 millimeters. Divided by t, the thickness of each side was 5 millimeters, right? So each side, so for example, for one of the sides, we have 70 divided by 5. The other side, again, we have 70 plus 70 divided by 5 plus 70 divided by 5. So basically, we have, this is a square section. So we have 4 times 70 divided by 5, right? So ds represents the side, each side, right? So for each side, we're basically summing up each side that we have. So ds 70 was, for example, the length of the median side of the square, right? The side of the median square, divided by the thickness of that side, right? Which in this case, all of them are the same, right? This is a square section with constant thickness, right? So 70 divided by 5. So 70 divided by 5 plus 70 divided by 5 plus 70 divided by 5 plus 70 divided by 5, or 4 times 70 divided by 5. And that's how this portion is here. So basically we add them all together and remember where the parentheses are, right? The parentheses here, the parentheses. So remember, see, dc over dp includes everything else, right? So you don't, for example, just close the parentheses here or close the parentheses here. No, we have to include everything else, right? Whenever you open the parentheses, whenever you open the parentheses, you have to end it at the end here, right? For this case, in this case, right? So say dc over db, the rest. You say dj over dg, the rest. Whatever we have after this, okay? So at the end we end up with 0.302 radians. The question also asks about theta j with respect to a, okay? Theta j with respect to a. How can we do that? Okay, so we say, we start with point j, which is a little bit odd. So we usually start from like one point here so that we can go forward, but here we are given point j. So if we want to move from point j forward to point a, we have to move to g. So what did we do before? We said, okay, the diameter, here we have a gear change, right? So we usually go from dg to dj, right? We said the next over the current. dg over dj multiplied by, open the parentheses, as we did before, theta g with respect to f, theta f with respect to e, theta e with respect to d, theta d with respect to c, as we have here. Plus another gear ratio. So we take the next diameter divided by the current diameter, db over dc, okay? db over dc multiplied by theta b with respect to a, okay? Easy as that, okay? So here, again, we open up the formulas. The formulas are pretty much the same as we had before, right? So it's T, L, J, G, J. You see, like, all of them is the same, right? And as we know, like theta c with respect to d is the same as theta d with respect to c. Theta a with respect to k is equal to theta k with respect to a, right? These are basically same thing. And yeah, so we talked about these before. So just basically now have to substitute the values, right? So we have again 150 over 200 multiplied by, we discussed these before, and here, yeah, we discussed these as well, right? So all of these values are discussed before, we end up with this value. Now, the last question was asking about if we were to use the same amount of material, what would be the dimensions of an equivalent rectangular shaft with B over A of 2. So what does it mean with the same amount of material, right? Sometimes they can ask you for it with the same cross-sectional area, basically. But what we can do is to find the volume, right? Because we're using the same material, right? So we can just use the same volume, right? To basically find an equivalent volume of the same material, right? Because the material is the same, so density, everything is the same, so the volume is going to be the same as well. So if we find the volume and we equal it to the new volume that we're going to find, then the new dimensions that we're going to find, you know, that from that we can basically find our dimensions. So we know that the volume of CDEFG that we're going to find is volume of CDE plus EFG. Why did I do it like this? The reason is portion CDE is solid, EFG is hollow. So calculations are different. So how can we approach that? So we'll say, okay, what is the formula for a volume for CDE? So this is a hollow, but this is a solid circular section. So we know for volume, we have the area of the base, right? Area of the base multiplied by the length. Area of the base multiplied by the length, 10 meters. So pi over 4, this is the formula for the area of a circle, right? So pi over 4 times diameter squared. Or you have pi r squared, right? Pi times radius squared, or pi over 4 times diameter squared, okay? And this diameter, where do we get it from? It's given in the question, right? So this shaft, solid shaft CDE, has a diameter of 100 millimeters. Okay. Plus, of course, the volume of EFG, right? So we have pi over 4 times basically this is the area, right? Pi over 4 times the outer diameter squared minus the inner diameter squared. This is the area of the hollow circle here for portion EFG. Multiplied by the length, right? 5 plus 3, 8 meters. So from that, we get this value. So this is the total volume used for this shaft. And of course, we are neglecting these portions, right? Because we are not interested in them. So volume of CDEFG should be equal to the volume of the new rectangular shaft we are trying to find, because we are doing the same amount of material. But what is the volume of the new rectangular shaft? Well, we can say that, okay, the same rule applies, right? The volume is the area of the base multiplied by the length. So the length, because we're using this uniform amount of material for the whole thing, the uniform geometry. So we can use the length as GFEDC, right? The whole length, which is 3 plus 5 plus 5 plus 5, or 18 meters. But what about the area of the base? The area of the base is basically the area of a rectangle. So it will be, if we consider one side A, the other side B, it's A times B. But wait a minute, here the ratio of the two sides are given. B over A is 2. So when we say A times B, for B we can substitute 2A, right? For B we can substitute 2A. So from here, basically we have one unknown, right? So we can basically divide this value by this and by 2 and take the square root to find A, right? And of course, remember, what units are we using here? We're using meters, right? We're using meters. So when we have meters, this value is in meters. So the value we end up with is 55.4 millimeters for A. And of course, B is going to be 2 times that value, right? 2 times 55.4. Now that we have this, we can answer the question, right? The question says find the maximum stress for this portion. So the maximum stress for this portion is going to be, again, what is the maximum stress for a rectangular section? It's T over alpha A squared B. T for that section, the maximum is 12.88. So because, as you know, the question said use the original torque diagram, right? So the original torque diagram is applicable for this. So what was the maximum value? 12.88, right? So as you can see here, again, I'm using the maximum value here because I'm trying to find the maximum stress value. And I don't need to divide like the shafts into 2 parts in this case as we did before, because in this case, I'm using a uniform geometry for the whole shaft, like CDEFG, for the whole thing. So there's no solid part, there's no hollow part, everything is solid, a solid rectangular part. So I can use just 12.88 times 10 to the power 6, which represents the whole shaft, divided by alpha A squared B. So we know A, right? A was 55.4 squared times 110.8, which is B. And this alpha represents B over A value of 2, right? So if you go to the table, for B over A of basically 2, you can find alpha of 0.246. And as you can see again, I'm using Newton and millimeters, right? Because as I said, for stress values, I always use Newton and millimeters to end up with megapascal and to avoid usually any type of conversion. So here I have Newton and millimeters. Of course, when I say not any type of conversion, the only conversion you have to make is this torque value, right? So you just have to multiply it by 10 to the power 6. And basically we find the value, the stress value here, 153.96 megapascal or Newton per millimeter squared. So here in this case, we can basically use the factor of safety formula again, the allowable stress divided by the applied stress. The allowable stress for steel was 300 megapascal. The applied stress, we found it here. So we find this value, which is greater than 1. So it's okay. So that's it for this question. So basically to review what we did, we basically identify first a value that the question gives us. So in this case, the question gave us a value of basically, if you remember, it was, I think, 150 megapascal for one portion. So from there, we basically found one of the torque values and we basically assumed some sign, and then we found all the other torques and found all the torque diagrams. And after that, it was just a matter of applying all, basically the formulas to, applying the formulas based on the values we know from the torque diagrams, right? And after that, we found the power based on the power formula. Of course, we used the power formula based on shaft AB, which was the shaft through which the power was supplied. And then we went and found the friction forces based on torque value divided by the radius for each gear, right? And of course, we know the forces between the two gears, action, reaction, they're the same value. And then, of course, we found the maximum stress for each shaft, again, based on the geometry. We have, for example, for solid shaft, we have TC over J. Hollow shaft, the J is, of course, different. We have the formula, for example, for a thin-walled section, we have T over 2 TAM, and so on. And then we, of course, found the factor of safety based on what you see here, allowable divided by applied. And also we found the rotation formula, as we know how to deal, you can go back to see like how we deal with basically when we're, the most important part is basically how we change from one gear to another, right? So we're transferring from one gear to another, as we said, the next one divided by the current one, diameter, and multiplied by parentheses, whatever the rest, right? And the last part that we did was to basically evaluate to see what is the effect of changing the geometry, right? So we had some part solid, some part thin wall, but some part hollow, and we change all that part to a rectangular uniform solid section, and we see how that affects. And of course, as you can see, also if you can notice, the stress here that we get is higher, right? For both, either of them, for solid or I believe hollow sections. But again, like, that's not the question, so we just find whatever the question asks. So from here, again, the factor of safety is greater than 1, so okay. And yeah, so that's it. So as you can see, the questions are all pretty simple, but first you have to deal with the torque values, and after we deal with the torque values, everything just is solved by itself, okay? And that's it for this video. If you enjoyed the video, please like and subscribe down below, and subscribe for more content for structural engineering problem solving, and I'll see you next time.